Okay, started the recording. I stopped transcription, so we should be good to go. Thank you again for joining the session. I'm going to be looking at this screen to present, so let me turn my camera off. I can come back later. To begin with, this was a talk I had put together to give to university students. I wanted to give it inside Intel for multiple reasons. Number one, I wanted to give the talk to get feedback. There are many people like David, who can probably give me additional pointers on what to add, what is more interesting, maybe many important items that I'm missing, etc. Number two, if there are younger engineers joining the session, they might have heard about many of these individual pieces here and there. I wanted to present an overarching arc that we should promote, talk about in the general community, be it in universities, be it your own family, friends, in any other venues that you can think of, so that people get a better idea of what companies like Intel bring to the world from the semiconductor manufacturing point of view. And number three, I also wanted to encourage our tech leads to come up with topics of this kind that can be presented outside. There are often opportunities. Intel interacts with universities, often looking for people who will go and give talks to the community. And while we do that, I'm kind of keen on making sure the slides we put together also look visually pleasing. They're all not like boring white background, black text, simple slides, but something that's more interesting. So I wanted to bring that aspect also to the table. On top of that, I do want to say that anything that we present outside need to have clearance from Intel legal. So one way to make that burden simpler is to present only material that's already available on the internet. So every slide that I'm presenting here, all the content, they're all mostly derived from either material that's publicly available, not from inside Intel websites or SharePoint sites, or material that have already been explicitly cleared and presented outside in conferences, etc. Right? So that's something that we should keep our minds on. So to get going, to those who may not know me, my name is Sundar Vedantam. I'm in Allentown, Pennsylvania. Been here for a couple of decades. My team works on the DLB part of the Xeon devices. Of course, this talk specifically is not anything to do with our specific work, but overall what's going on in the industry. Anytime we present anything outside Intel, we should also put these notices and disclaimers, so I keep that in my slide. And again, when we present outside, it would be good to promote this particular site because many people still don't know about it. Even amongst your family, friends, even nephews, nieces, whoever is interested, you might want to point them to networkbuilders.intel.com website, which is a free site that Intel maintains that's accessible to anyone in the world, including university students and faculty, that has about 400 courses students can take. So when we say course, it's basically just 1 or 2 hour long lectures, something like what I'm doing right now. This is not just to promote Intel technology, but also to disperse and share knowledge in the wide range of topics that we work on. Could be like mobile computing, AI, ML, security, and so forth. And each lecture has at the end as a short quiz that one needs to take to complete the course. And once that's done, you can actually follow through. So for example, if you are interested in security aspect, there'll be what's called a pathway that's put together, stringing together maybe 15 courses that you can take in a sequence. So you will finish a custom pathway to get certified in that one particular area, right? So mobile computing or security, something like that. And there are about 1,400 different custom pathways that are available. Intel does not want to charge any fee for using this service. It is maintained professionally by a team of engineers inside Intel, but we don't charge any money for it. It's just a promotional thing Intel does. But as a result, any certification people get stays within this domain, within Intel, right? If there are students interested in getting a digital certificate that they can attach their resume, etc., the same courses are also cross-posted and offered via Coursera. So they can take it, and there you may need to pay a small fee, and then Coursera will give you a digital badge that you can attach to your LinkedIn profile and so forth, right? So please promote that outside when you get a chance. So in this talk, we will talk about where are we and what are the optimization vectors that we continuously work on. And then we'll talk about packaging trends and how is that going to push the envelope to go much further than where we are currently, and present the takeaways in the end. Okay. So we'll talk about 4 or 5 different orthogonal vectors. So initially, let's start with the clock speed. People who have been around the 80s and 90s, we all may remember initially that even the home PC or any processor that's coming out, they all need to be, they all used to be advertised using what is the clock speed at which it's running, right? So way back, it might have been 1 megahertz all the way in the 1970 kind of time frame, and 80, 88, etc. came up. In the 80s and 90s, you will constantly see 100 megahertz, 120 megahertz, and 200 megahertz device and so forth when the Pentium era, all those devices were coming out. If you notice, this is in log scale. As a result, when you come to around 2003-4 kind of time frame, we were in the maybe 2.5 gigahertz kind of frequency. But as you can see, we kind of plateaued out at that point, right? We didn't continue to proceed going to like 10, 20, 100, 200, 500 gigahertz clock speed anymore. It kind of plateaued out at that point, right? So initially, to improve performance in CPUs, clock speed, basically speeding up the clock, and so things get done faster, was the main big knob that we had. And again, this chart, these are all taken from public domain. So you can see the clock was really ramping up more or less linearly through the 80s and 90s and 2000. But somewhere around 2004, 5, wherever we are, and we are kind of stayed there. We are not going any more beyond that, right? Why is that? That's mainly because, number one, the heat that it generates, right? So as you go faster and faster, you can open and close the transistors, the gates faster, things get done faster, true, but it also generates enormous amount of heat. And how do you dissipate that much of heat became a problem, and it became untenable. You cannot continue on that path anymore, right? So that's why we kind of had to put a stop, or like keep that at that point and not proceed beyond that. That's one reason. There are also other reasons. If you can think of the circuitry that's inside the device as wires that are going from point A to B, they form capacitance, right? And when the device or the gate need to open and close, the devices need to get charged and discharged, and there wasn't enough time for the capacitance to actually drain. That resulted in very difficult computing situation where you don't, the clock has become so small. I mean, the time window has become so small, there is not enough time to drain the circuitry fully. And so computing basically doesn't work, right? So you can't keep turning that one knob continuously more and more. So that's another big reason. The third reason is this eye diagram. Many of you, if you worked on any hardware area, you may be familiar with that. If not, this basically, since it looks like a human eye, it's referred to as eye diagram. And what this shows is the voltage in the circuitry going up or coming down. So when it is a digital circuitry for 0 and 1, we just presume kind of a step function. That is how we are taught how 0 and 1 is recognized, presence of a voltage, absence of a voltage, presence of a voltage at like 1 volt is, let's say, 0, 5 volt is 1. So we usually think it's perfectly at 1 volt, and then at the next instant, it's instantaneously at 5 volts, and that represents 1 and so forth, right? But in reality, because of capacitance, because of the charge time it takes, etc., it doesn't go in a perfect step function, but more like it raises like that, and then it drops like this. When it does, we do need to find some threshold, some point after which you will call this as 1, maybe somewhere here, and then somewhere here, if it goes below this point, you will call it 0 and so forth. But if the clock is so fast, then this eye diagrams start to kind of shrink. So hardware engineers call this as opening, the eye opening start to shrink, right? So it doesn't have enough time. It just goes up, and before it's over, it has to come down. And so recognizing when it reaches 1 and when it is 0 becomes more and more difficult, right? So you want a really big ideal step function with a broad opening in the middle of your circuitry for you to be easily able to recognize 0 and 1 state, and that doesn't become possible when the clock speed is really, really high, right? And after that, there's one more reason. For computation to work, we know each one has, let's say you want to add 2 numbers, we know it gets broken down into multiple instructions. That's the famous x86 instruction set that we are all very familiar with. And so you may need to go fetch the number from a register, put it in another register, get the second number from a third register, do the addition, and then go back and put it back into the fourth register and so forth. This can happen, but each one takes a little bit of time, right? So the time it takes for the particular action that takes the maximum time need to be the gap, the time window that you need, that the clock has to accommodate, right? So this is like T1, T2, T3. Let's say these are all the clock ticks. So you have revved up the clock to, let's say, 2 gigahertz. So this T1, T2 is like the inverse of that. So it shows you how much, what microsecond, nanosecond time that you have. So each one of the instructions that you intend to complete need to get completed by the circuitry within this particular time window. If it gets done properly, great. And then you go 1, 2, 3, 4. Maybe this add instruction is done. Maybe there's a multiplication instruction that is done, and so on and so forth. But within that, if there is one particular instruction 3 that takes more time than instruction 1 and 2, your clock cannot run faster than this time window, right? Otherwise, this instruction is not going to get completed and you are in trouble. And how do you solve this problem? One way to do this is to break this particular activity itself into 2, and then you can potentially, let's say you break it into 50%, and so you can actually bring the clock this much closer. And so whatever time that is all getting wasted here can all be recovered and you can do more. But you can do that only so much. I mean, within the x86 instruction set itself, there are a lot of things that takes multiple clock cycle steps, 20, 30, to get something completed. So if it becomes too large, the return on that improvement starts to diminish. And so you can't go too much in that direction either, right? So all these puts a limit on how far you can go turning the clock speed knob. So it kind of went there, and even now it's possible to turn it a little bit more, but not endlessly. It's not infinite, right? So we need to start looking at some other vector. And that's where we started introducing the multi-core and multi-thread model. And as you know, I mean, now this is a pretty common idea, but in the 90s, when we had only one CPU core per CPU, and then introducing this multi-core in the early 2000 was all a big, great path-breaking idea, right? So this came in, and in case if you are not aware of the difference between core and thread, thread is like the operating system that is running two different threads and switching back and forth between the two threads. That also makes it look like you have two different cores within that. So you can have one core, let's say you run two threads, so it starts to look like you have two cores. But you have two cores and each one running 4 threads, it starts to look like you have 8 cores potentially, right? And when this was introduced, of course, there were some fun that was made of companies like Intel saying, oh, they couldn't improve the clock speed anymore. And so they've stopped saying that and they are pushing this new idea kind of thing. But that had to be done, right? So we had to look at different vectors that could be optimized. So we are all familiar with this, so won't spend a lot of time, but you can look at this. So one after another, various Intel core technology as it came in, they all had different cores and thread that were introduced, 4 to 4 all the way to 18 cores and 36 threads and so forth, right? So that increased the computing capacity considerably. But can we keep going, turning that knob continuously? Again, you start hitting the limits on that as well. So you can't have like 10,000 cores and 10,000 threads on each one, because what you need to do then need to be split into all those cores, get done, and then brought back together. And at some point, depending upon your use case, what's the application that you are running, that becomes impossible as well. And again, just like clock speed, there is, it's not like a hard stop. There are companies out there designing chips with like 200 cores, 400 cores, etc., where the cores are extremely small. They do very limited amount of stuff, but they can do things in parallel. You can do the SIMD, single instruction, multiple data kind of thing. So there are applications and you can do that. But for general purpose computing, you can't keep doing, okay, we had like 100 cores, now we'll have 200,000, 10,000 cores and so forth to continue pushing the performance, right? So it starts to plateau out at some point. So we need to start looking at some other model. So then, of course, our own TikTok model comes in. This was again introduced by Intel. In case if you are not aware of it, it's called TikTok because we kept doing two different things. One is the shrinking the node. So maybe from 65 nanometer, you all know now we are in the Intel 5 nanometer kind of thing. But I'm talking about 65 because in these range, this TikTok model was really working well, and Intel kept making a lot of progress. So 20 years back, when I joined the industry, 128 nanometer was the standard, right? From there, we jumped to like 96 nanometer kind of thing. It all looked fantastic. But even moving further, so there was like 65 nanometer, and then we'll make a process node improvement going to 45 nanometer, and then another jump to 32 nanometer and so forth. Simultaneously, the architecture team would continue to work on fine-tuning the instruction set, the x86 instruction set. So we may work on introducing new instruction, modifying the architecture, getting things done in a more efficient fashion, and so forth. When we do that, these are two different variables. Then Intel didn't want to introduce the change in the process node and change in the microarchitecture simultaneously, because when the new device comes out, if it doesn't work properly, you wouldn't know whether we messed up on the node front or microarchitecture front, because each one is quite complex. And just to reduce the risk, we introduced this TikTok model where each one of the tick will introduce a new microarchitecture, and the talk will introduce a new node change. right? So let's say we are in the 65 nanometer. Things are working okay. We've pushed out a couple of devices. Then we'll change the microarchitecture, introduce it at the same 65 nanometer level. So this would bring in another boost in performance. So once this stabilizes and we have pushed out a couple of devices, then we will introduce a new node. So we'll go to 45 nanometer, but keep the microarchitecture the same, right? And then after a couple of years, then we'll again go to a new microarchitecture node, but keep the process node the same. So we'll keep flip-flopping this way. And this worked out really, really well for several years. And so we went from like 45 nanometer to 32 nanometer, 22 nanometer, and each one had these microarchitecture introduction in between and so forth. Okay. Again, some of these technology may look a little older. That's because I was picking up material from the internet, just not to reveal anything that's too new. But it serves the purpose of showing what we are focusing on. The tick-tock model, where the microarchitecture and the process node technology comes back and forth, pushing the performance further and further away, right? This is great, but again, as you know, after we hit like 10 nanometer, etc., we started introducing newer and newer changes, but that's not exactly on the nanometer scale alone. We introduced like FinFET technology, ribbon FET, things like that, and then Intel kept calling it as 10, 10 plus, 10 plus plus, 10 plus plus plus, etc. Whereas the other competitors have started calling that correctly or incorrectly, mostly incorrectly, as 7 nanometer, 5 nanometer, etc., making it look like we are not progressing well. And so we also have to introduce our own nomenclature, saying 10, Intel 7, 4, 3, 20 Armstrong, etc. But this is also kind of hitting some limits where introducing, I mean, we are still continuing. As you know, we have 18 Armstrong coming out beyond that, etc. But still, what more, what else can be done becomes a question. And each time we introduce a new process node, as you must have heard, initially the yield tends to be quite low, right? That is because it's a new manufacturing process. You introduce the technology and then start creating the devices, and then you start testing them. They don't work really well. And so what do we do with that? If you just leave it at that, of course, the profit margin is going to start dropping dramatically. We don't want that. And of course, the design engineers are going to work on improving the technology so that the yield continues to increase. But in the meanwhile, what can we do to keep that yield going? First one, Intel does enormous amount of research and development in doing wafer testing, right? So I hope you all clicked on those 2-3 links that I included in the meeting invitation. The first one talks about how we take the basically sand, melt it down, and then create those ingots, and then cut them down into individual wafers where things get etched in. And when they come to our factory, we start doing a lot of testing even before that becomes an actual chip. Just keeping it as a wafer itself, we attach probes and make sure the dozens and dozens of individual dies that are out there, individually they work okay, right? And if they don't, then we need to throw them out, and that's where the yield aspect comes into play. So we build a lot of tolerance to allow defects where possible. What do we mean by that is when you design a CPU, within that there may be like an ALU, arithmetic logic unit, or some computing unit, cache lines, a memory, and so on and so forth. But some items like the cache lines may be kind of very similar looking pieces that need to be replicated. So if we need to put, let's say, some 20 units of some memory, we might actually put 25, 30, something, increase it a little bit more. So during testing, if we can identify some parts of the memory cache that's not working, we have technology to mark that out, not use them, and then still use the remaining one with the added redundancy, helping us reach make that particular die still usable, right? So we allow we build in some tolerance by replicating some parts where possible, and it's not possible to replicate everything completely. So beyond a point, we need to throw away if things don't work okay. But we do work on optimizing the design at that level. And second thing that we do is binning. Many people may not have be very familiar with this idea because when it comes to microprocessors, we tend to think that they're all 100% identical pieces of silicon developed, and then we just put it in packages and ship them out. Not really true, because even at that level, depending upon how well the process worked, even though it's all incredibly complicated, sophisticated, we have made it so fine-grained and so forth, still there are small variations in how things work. And so we actually test individual pieces at the wafer level, at the packaged level, etc., to figure out how the individual pieces are working. And even if you take any of the, let's say, i7 core i7, core i9, any of those, that completed chip, when it is tested, in some cases, they may have slightly more leakage current, which means it's perfectly functioning part, but it's going to consume a bit more power than another device coming from the same production line that may be perfectly built. As a result, it consumes or it has very less leakage current. So if you put that on a circuit board and use it, it will work perfectly, no problem at all. But the first device will consume slightly more power compared to the second device, which has less leakage current, right? So when we notice these, we start putting them in different bins. And so some customer who is very sensitive to the amount of power consumed by the device, maybe it's a huge data center operation where they want each one of the device to consume as little power as possible, and they are willing to pay a premium for that, then they will get the devices shipped from that first bin, right, which has the best parts. Whereas the second bin, third bin may have more and more leakage current. On the other hand, maybe if it is going to be used in, let's say, one laptop or one PC, something like that, if it is consuming a little bit more power, maybe it doesn't matter to that particular manufacturer. If so, they might be more willing to take the parts from the second or third bin, paying a little less because it doesn't matter to them. So we sell the parts sorted out that way, binned in different bins depending upon how good they are, and charge customers differently. Right? And then we also, in the rest of the part, we'll discuss more to get into this chiplet idea. So if you looked at that original videos that I sent, usually the wafers that are put together, they may be, think of it like a foot-long wafer, right, in which the chips are etched in, and then they are broken down into individual dies and packaged. And normally, to add more and more computing capacity to those individual dies, if you keep doing that, then you need bigger and bigger dies, right? Because you are adding more and more computing capacity. I mean, think of how much was there 20 years back versus now. So for that much of computing capacity to go in, you may need to add more circuitry, more memory, more CPU capabilities, etc., which means your chip itself becomes much bigger. Of course, because we are doing Moore's law, we continues to push the limit on how we can make it smaller. That's moving in the opposite direction. Things get evened down a little bit, but still If you need more and more, then the chip size, the individual die becomes bigger and bigger. Now what happens is, since because of the node progression, we are trying to cram more and more circuitry into a small area, and the design of more and more capacity or like computing capabilities into one die makes the die bigger. Even if there is one corner little place where something doesn't work, that whole die becomes useless and we have to throw it out, right? That's the reticle limit, meaning that's think of it like the square piece of the die, where in one corner, one piece, something is not working. So when you test it, you are forced to throw it out. We don't want that to happen, right? Because that's why initially when we go to a new node, you end up seeing very limited amount of yield. So how do we solve that? That's where the chiplet idea comes in. Here, the notion is to create smaller pieces of dies that has maybe one particular feature function that works well, and then interconnect them using the latest technologies that we develop, so that the entire device need not be in one die, right? So you have multiple dies that you can put inside a package and make that your full CPU or your full device that provides all the features that you need, but that allows you to reduce the amount of wastage. Because think like if the original die size was x by x, now instead of trying to make that bigger die, you break it into 1/4 and you make 4 different chiplets, and each one does only some limited amount of stuff. And then you take different chiplets from different pieces and put them all into a package, then your yield issue goes away, because originally wherever you had one issue that resulted in that entire x by x size die to be thrown away, now you are throwing away only 1/4, right? The other 3 are still being used. So that allows you to increase the yield of the device itself. And of course, when we do this, then we need better interconnect and connect technologies to combine all these little chiplets to make into a bigger, broader one, right? So that's what all our new packaging technology that we keep hearing about is all about. So we'll get into that aspect that comes to packaging. Since I'm not able to see the any discussion, questions, anything that might have been post, maybe I'll pause here just for a minute. If there is any question, anything that I can answer. If not, we can continue. Okay, hopefully maybe there's no question. So the next few slides, I should give credit to Ravi Mahajan, who's an Intel fellow. If you're all interested in this particular topic of basically heterogeneous integration of different pieces going into one package, I'd highly encourage you to look him up on YouTube, where there are many of his lectures posted. This particular set of slides, I saw one of his hot chips discussion and reached out to him on a Saturday morning, and within an hour or two, he sent me all the slides. So my thanks to him. And his discussions get into a lot more detail. So if you are interested, please go look him up, right? So this heterogeneous integration, that's what this HI stands for. What this means is being able to take different pieces of individual silicon dies that have come out, and then we can mix and match whatever we get and put them all under one package and get them connected using the best integration technology that we have. That gives you the final product that you need at a very fast, expeditious manner, right? And to do this, we need to be able to put the actual computing pieces and the memory very close to each other. So there are actually two ways to do this, the interconnect, right? So one is to have the SerDes kind of interface where you have fast and narrow, more like a serial interface. You have like a very small number of wires through which you are sending the information in, and it can do it at really, really fast. So that's like a serial interface. Or you can go in the other way, saying wide and slow. So you have like much wider number of wires that is transmitting the information, but it's at a slower speed. So that's like a parallel approach to getting things connected. The fast and narrow, of course, gives you good bandwidth. It's probably easier to work with. On the other hand, the power consumption continues to increase considerably, right? So the wide and slow approach is what we continue to work on, and that gives you much better density where you can like stack a lot of things together, and the power increase is not that high, and that's what Intel continues to work on. If we push this technology for using this EMIB kind of ideas to connect them together, you can potentially take totally different nanometer node devices. So maybe an FPGA fabric that's on 10 nanometer, some CPU that is at 7 nanometer, memory at some other nanometer, and put all those chiplets together in one package and make that work as a completed device. And as you can imagine, that means each one of these each one of these dies are going to be much smaller. So the CPU die alone that is being manufactured at 7 or 5 or 3 nanometer, we can hope to improve the yield because it's much smaller. We are not trying to put everything in at that 7 or 5 nanometer new node die level, trying to get everything to work perfectly, right? It's a much smaller piece of silicon that needs to work properly. So that helps us improve the time to market as well. So as long as the packaging technology works really well, we can do this heterogeneous integration better and better, and that can take us a long way to pushing the performance without increasing the expense, without reducing the yield. We can keep going to the next level, right? So this notion itself, this heterogeneous integration itself, is not really new. It's been talked about maybe even a couple of decades back, but there were two issues. Of course, initially the notion was there, but the quality of the integration was not that great. As a result, we couldn't really use it for very high-end CPU type manufacturing, maybe for lower end products. And number two, a couple of decades back, the dies itself were okay. I mean, we were able to cram more and more and get the whole device built in one die kind of thing. And so there was not much of a need for heterogeneous integration. But now we are slowly hitting the limits on those vectors, right? And so now packaging is becoming really prominent, and it also has a lot of potential and a long way to go. I mean, we are only starting on that front. So in my understanding, at least for the next decade or two, it can continue. There is lot of runway there to continue improving it, right? So the idea is to do on package interconnect, high bandwidth signaling, power delivery, as well as thermal management. You can imagine as you cram more and more, there is always going to be thermal management issues. So we need to make sure things are all aligned and we are still able to take out all the heat and dissipate them fast enough so that devices don't just melt away. So the assembly process itself, so you need to make sure the components that we are trying to integrate will integrate, because if you really have like incompatible interfaces on like one part versus the other, how do you connect them? How do you make them work with each other is an issue. And of course, companies like ours, Intel, do a lot of work on this front, and we have published in like more like an open source kind of thing what the interfaces should be and how they should be designed, etc. So that, as you might have heard, we are going to be building maybe ARM devices. So if the ARM CPU design comes in, even if it's manufactured in some competitors' fab, as long as they comply with the interface requirements, we can throw it inside a package and then add our memory, our FPGA, whatever else, and then put a package together, right? So standards are being developed on that front. And materials and design tools. Actually, if you keep digging into it, it'll show like 1 or 2 quick videos. So even if you simply take substrate, what is the substrate on which the die gets placed and how are they getting built together? The substrate itself has so many different kinds. There is silicon substrate, there is ceramic substrate, there is circuit board kind of laminate substrates, and so forth. And each one of this can have different actual material, different conductivity properties, different thermal properties. So there is a lot of work that gets done in finding the newer material that will help us do this integration in a very seamless way, as if it's all just like one die, right? So that's the ideal goal. We want to make this packaging technology so smooth that the gap between die 1 and die 2 practically vanishes. So making them all look like it's all just one big die, which is what ideally we would like to do, but for the yield issues and others that come into play, right? And the using advanced packaging technology simply meaning how do we bring that in? So what are the technologies? So the two you might have heard recently is that EMIB and then Faveros. So things like that. So what is it that we need to integrate to make them all come together, right? So EMIB is that embedded multi-die interconnect. In simple terms, it basically is taking different dies and putting them in one 2D planar geometry, meaning in one surface, putting them together and then connecting them with each other so that they can serve as one device. And then we put one big metal casing around it, and then it serves as one device, right? So that is EMIB. Faveros, in simple terms, is going in the Z direction. So you can take die 1, die 2, put them on top of each other, and then interconnect them. And Faveros Omni and Direct, these are to basically combine everything together and then go in 2D and 3D direction to move forward. And when we do this, this bump pitch becomes important. I think it comes up in the next slide also. What this means is if you have one die, basically you pull out all the connection interfaces that it needs to connect to the adjacent next die out. And in the substrate on which this die gets placed, you will have something like pads, right? So when this die goes on it, just like in a simple circuit boards that you might have seen, each one of the device that we put on, it has all these little bumps at the bottom side that goes and sits on top of the pad that has the connection on the board. And once they make contact, we get the device working. The same idea, same notion gets implemented even within the device itself, right? So you have the device 1 coming in, and they have these bumps, and they connect with the connectors that are in the substrate to get them connected from one die to the other, right? And by reducing that bump pitch to making it smaller and smaller, you can tie them more tightly, more nicely together. So as you can see, the progression, so we are able to go down as low as like 10 microns kind of thing, which will basically blur the boundary between where the wafer ends and the package begins. So it becomes like one smooth continuous process. To get this to work properly, there are so many different aspects that need to be looked into. We'll just touch upon a couple of these, and in the end, the goal is to provide like this cost-effective, high-precision, quick-turn assembly devices, right? So bring different pieces of die and put them all in one substrate and get them to work. To get this to work, Intel does a lot of research work in this flow. This just shows from a high level, I mean, you have the wafer that is coming in, and when it comes to the factory, goes through a wafer sort. And this is where I meant basically we test the wafer to make sure the individual dies that are there are all good. And then we do the die prep, meaning that the individual pieces that we need to break off to put in individual devices, we prepare that. Then this KGD stands for known good die. And from some of the papers I read and the discussions I have seen, I understand our effort really makes sure that with all the technology that we do, most of the time when the wafer comes in, about 99+% of the die that comes in are all good to use when things are working perfectly, right? So that's the level of precision, making sure everything working okay, developing enough tools to test, making sure that the wafer process, etc., are all okay. Everything comes together. Then we bring in the substrate on which the die gets placed, so the assembly gets done. Then we put that casing on top of it, do the testing, finish, and then ship it to actual board development where it gets put on, right? So that's the whole process it has to go through. And when it does, then we need to make sure it still is very power efficient, high bandwidth on package IO links. That's what we talked about. So it could be the serial or parallel version, enable a diversity of off package IO protocols. This means later on, let's say we are doing an ARM CPU sitting inside, maybe an x86 CPU also, or maybe an FPGA, everything that needs to come together, then that means all the IOs, the protocols, everything need to work together. Deliver noise isolation for single-ended differential signals. That means if each one of these things, they are all so close to each other, if one component generates more heat versus another one that is sitting next to it, we don't want the substrate warping, right? We don't want the heat from this affecting the performance of the adjacent die, etc. So a lot of materials technology research development needs to go in to make it all work together. So there are, you can see each one of this. I mean, people can do PhDs on these, right? And they are doing it. And there is so much more to do to get this all to come together. So this is just on the high density interconnect itself. This is what we are talking about. So this is a die, and you can see each one of this at the die edge. These are the actual wiring lines that are coming in, and these are called the bumps that we mentioned below. And if it is just like horizontal lines, this is linear, right? So you can just put one after another. But for you to actually make the connection, you need this little bump which has to be put on top of each other to make the connection. But if you need to do this, then this has to be bigger than this. So how do you make sure they all they're like densely packed as much as possible? So there were research going on in things like how do you reduce the width and how do you reduce the space, pad reduction, etc. And we have made progress from using like solder to copper, right? Maybe a little bit more expensive, but it gives you more dense packaging that is possible. And when we do things like that, then we are able to put die 1, die 2, and then connect them together to like start packaging them really close to each other. And how close can we get in packaging? These numbers are all kind of astonishing to me. I hope I convey this, that how awesome these are to you. If you look at this, this is the traditional organic package, meaning in like within 1 millimeter, we are able to put maybe about 50, 30. Yeah, this is 100. So this is about 30 wires next to each other, right? So within 1 millimeter, we are laying 30 wires next to each other. As we keep moving this way, there is high density, and then using technologies using silicon backend wiring. When you go all the way, look at this. We are already reaching 500 now. We are pretty close to 1,000 wires can be put next to each other within this 1 millimeter in one layer, right? So this is what all these lines are. And this is this half-line pitch that we are talking about, meaning you need this bump, you need this next bump. So from here to here, how much space? So we are constantly trying to reduce this as much as possible. So if you don't need a bump, or if you can make it much smaller, then you can pack more and more things more densely, right? So right now, all these are standard. So depending upon which technology that you pick, whether it is this is flip chip ball grid array, this technology versus this, you can have lot less or lot more number of wires that can be laid next to each other. So when the Intel Foundry Services goes into production, this is what will happen. So technically, maybe one die that is manufactured in competitors, one Samsung, TSMC, something that may come in, and we can put that in and choose the appropriate connectivity and connect that to other components within that same package to make it all work like one seamless single die device, right? So the focus is increased interconnect density and improved power efficiency for increased bandwidth. So basically, the more wires that you have, that's the parallel connectivity that talked about. You can push a lot more information from the, let's say, the CPU to memory, and that kind of exchanges, right? And the same idea applies even in vertical interconnect. So you can see again the number of bumps per millimeter square continuing to rise as the research effort continues, right? And blending that 2D and 3D. So like we said, 2D is the MMIB technology. So maybe this is a good point to show one brief 2-minute video that explains why, how EMIB technology works. Again, these are all videos that I picked up from YouTube. You can look it up. Let me play this one. Hope that makes sense, right? So, and initially that EMIB was introduced more like a 2D technology. It's called sometime 2.5, since there are additional layers beneath that, that is trying to interconnect adjacent dies in the substrate. So that helps you reduce the reticle limit and make like smaller chiplets all connected together. And a couple of other videos that I sent also talks about how power delivery architecture is also getting improved, basically separating it out. I mean, imagine for each one of this gate that's there, for things to work, you also need to be able to supply power, right? The voltage that's going in to make the gates open and close. To do that, even there is a lot of work that goes on. So these are all different vectors through which we are trying to optimize and push the limit. So in the historical approach of power management, meaning 80s to 2000, we did frequency scaling, meaning we were able to turn the frequency knob, make the clock go faster. And that resulted in this threshold voltage also need to be raised up, right? We said since the time that's available is much smaller, from let's say from 5 microsecond, it becomes 1 microsecond. You still need to detect in that eye diagram that I was showing where is 0 and where is 1. So one way to do that is, of course, you work with like larger voltage. And so instead of, let's say, 1 to 5, let's make it 1 to 10, just to give a silly example. And so again, if you're sensing the 0 and 1 at 1.5 volt and 4.5 volt, since you are working with 10 volt, even though the clock time is small, it can quickly ramp up, and you may be able to detect that one state and still work well. But as a result, you also end up with very leaky design, and that consumes more and more power, right? So that will heat up the device much more. And when you shifted to multi-core models, instead of one CPU, now you have like so many CPU cores in the system. That means you need to provide these power rails separately, taking power to each one of those cores within that device. And this simple diagram shows client power rails, meaning on the client side devices versus server rails. And you can see by 2019, in one device, you need like some 53 power rails. These are all like extremely complicated. And how do you I mean, the amount of design optimization, etc., that you need to do to get all these power rails delivering power to all the cores simultaneously, that itself becomes so complicated. So what is the solution? There, Intel has introduced this fiber. It's called fully integrated voltage regulator. And what this basically means is, forget 10 volt, 5 volt, all that. Now we really work within the 0.5 to 1.3 volt, right? So that the whatever voltage that you are supplying, it gets taken down, and inside that, for the 0 and 1 things to work, it's from like 0.5 to 1.3, meaning very, very low voltage variation going up and down, and that itself allows you to recognize that 0 and 1 state. And if you can effectively do that using integrated voltage regulator within the device itself, the leakage current reduces, and the amount of power that is needed to do the computation reduces, and you still get to do the same amount, I mean, the same amount of computing capacity built in, right? So if you go in and look at that papers, initially when this fiber was all introduced, the reduction in power was all considerable. I mean, more than 50-60% power reduction happened. But of course, it also makes it more and more difficult. There's no one clear knob that you can keep turning, right? So you can't make it from 1.8, you went down to 1.3, but you can't keep going down to 0.2, 0.1, etc. You do need some voltage for things to flip its status from 0 to 1. And when you do that, bring in multiple pieces and then tie them all together. I think I mentioned this even before. There are issues like thermal crosstalk, meaning if this is manufactured using a different node, that is using a different voltage, the amount of power heat it's going to generate, that may affect another device that is sitting next to it, developed in another node technology, etc. So this die-to-die thermal resistance, the thermal crosstalk, all that need to be somehow managed. And how do we do that? Again, we go into the actual material. I'm mentioning this because many of us work in software or like the actual design, etc. But behind the scene, we may be, I mean, there are Intel engineers working to switch the material used in the substrate from one material to another to see if the thermal property improves and if you are getting better distribution, etc. Right? So low resistant die-to-die thermal interface, those are being used in this Foveros packages. Best-in-class metallic thermal interface material. So we constantly work with companies that specialize in these kind of material to see what is it that we need to switch over, switch out, and so things will work better. And this is even towards making things environmentally friendly, etc. So I mean, as you might have heard, Intel is one of the first companies that got rid of lead because we stopped using solder and then it started using copper to make those bump pitch, that connectivity, etc. Right? So trying to be like optimize, make things better, also move things in the right direction, making things less poisonous and so forth. I mean, I can even go one step further, saying Intel advertisement that are out there, you might have seen saying our processors are all conflict free, meaning you might have heard about like conflict-free diamond, etc. So from wherever it is mined all the way when it becomes jewelry, they usually do a custodial supply chain tracking to make sure nobody is abused, everybody is paid fair wage, blah, 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 etc. to make sure that, that they are produced ethically, humanely, the right way. And Intel does that and certifies that the processes that we sell are all conflict free, right? So all the material technology that we use are all sourced ethically, humanely in the right way. So you can see in how many different ways these things sprawl. We can keep talking about that continuously, but coming back to the technology, just if you just take thermal properties alone, there is so much of work to be done to make sure this complicated packaging technology will not end up heating things incorrectly and giving some issue in the field because of incompatibility, etc. Right? So main things that we should remember is when it comes to packaging, EMIB 2D, right? Foveros 3D, so you can put die 1, 2, 3 and then interconnect them back and forth. And then now we are able to connect EMIB and Foveros together. So you can do 2D and 3D stitching together to make packages that can come together, bringing in all the technology continuously. There's one more quick video that talks about how Foveros technology works. Let me play that. Yep. So in the latest device that we are pushing out, you all may have heard about Ponte Vecchio, which is the Sapphire Rapids, but data center version of the device. So that actually combines the EMIB 2D and then Foveros 3D technology together. So that really has these compute tile, Foveros, base tile, Rombo, blah, 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 memory, etc., all together. And this one package ends up with like 100 billion transistors and actually 47 active tiles. By active tiles, we mean that there are like the computing parts. It's not just some substrate kind of thing, right? So 5 different process nodes, and we are able to blend them all together to make one package that comes together, serves as a combined version, right? In my mind, I mean the value that we bring in like pushing this in so many different direction to bring more and more computing to the world is like simply fantastic. And when I go to universities, etc., I hear that even students who are really interested in computer science, when they come in, their view of working for a company usually stops at like Apple or Google or something like that, right? But the value that semiconductor industry brings in is actually so much more, and that's really often not felt by younger kids or society at large. So I really think we all need to make use of every opportunity we get to go push this message, right? So just from the packaging point of view, quick summary is that the heterogeneous integration, that's a key enabler. The Sapphire Rapids took a while and it got delayed and all that because it's one of the first devices that used this packaging technology extensively, right? So now that we've got that working, hopefully the future devices will start coming out faster. Hopefully Emerald Rapids, all that seems to be going well. So we'll continue leveraging that notion and like facilitate power efficient, high bandwidth die-to-die interconnect. These are all needed, right? So if any one of them don't come together very well, packaging doesn't hold up its promise, right? So we need to keep doing that. The power supply, like we mentioned, you saw like how many rails in server packages, 50 different rails that need to be delivered. In one of the other videos that I mentioned, there is more discussion on how the power layer is separated out and how it manages to deliver it to different components of the device in parallel. So getting that done, and in addition, using the correct thermal management techniques to bring different tiles to come together, even though they may be of different nodes, different technology, still making them all work together, eliminating any thermal resistance at the border of those dies, right? That's also a big contribution from the packaging technology. So you can see it touches like materials, tools design, power delivery, voltage regulation. So much goes into getting packaging really working well. The end goal, of course, is to make it practically invisible, right? So that as if we have designed everything in one big die and everything is working so very well. So this is expected to be a big frontier that will keep pushing us forward. And of course, Intel is not the only one saying that. You can see like a lot of academic papers and other companies, competitors also realizing that this needs to be done. I mean, there are no other companies saying, oh, we have this one knob and we are going to keep turning it continuously, right? So everybody is coming to this realization. That's because as a like overall total takeaway, that persistent need for high performance and low power, that's going to continue, right? I don't know if you all saw some recent articles, things like ChatGPT or any of these machine learning AI-based tools, unlike, let's say, Google search, where the entire web is already crawled and indexed, and we have the results. And when you are doing a search, it just needs to pull out a result and show it to you. Compared to that, the new AI-based tools, each time you give it a prompt, it actually goes and runs a lot of computation and then gives you the result that you are looking at, right? As a result, there is lot more computing involved in this ChatGPT kind of search, or like the results that are delivered to you, compared to the traditional search engine kind of look up and deliver kind of result. So there is this another big way of computing need that is coming in. I actually read articles pointing out how smaller companies, startups trying to do ML AI based services, they are struggling because their solutions work well initially, but as the user base continues to go up, the amount of computing that is needed to serve them shoots up considerably. So it's actually putting a barrier on entry for smaller, newer startups. And so only big established players with deep pockets can currently serve that need, which means there is still a lot more requirement for increased and varying computational loads in the world. And so Intel kind of companies need to keep pushing that, right? And for us to do that, we looked at all these different knobs that can be turned, but there is no one knob that we can keep turning. So currently, it looks like the combination of different vectors need to come together to keep pushing the limits further. But we are not at the end, right? So at least the packaging ones that the papers I read or lectures I listened to the extent I understand, we are just starting. So there is still a long way to go before we hit the end on this one. So good area for younger engineers to get into and do some real good contributions, right? So since we still have a couple of more minutes, I usually play this one more video that talks about this ultraviolet lithography one, and then we'll wrap it up.
In the 21 years I've been reporting at Intel, I've seen amazing products and the machines that help create them. But the machine I'm about to show you blows my mind. Come with me behind this door, and I'll show you. This is it, an EUV, or extreme ultraviolet lithography system.
It is likely the most complicated machine humans have ever built. It pushes Moore's law forward, and chip makers cannot produce leading-edge chips without it. But more on that in a moment. The EUV machine is a reality after 35 years of sustained research and development from lithography leader ASML, Intel, TSMC, Samsung, and others. Delivering just one of these tools to Fab D1X in Oregon took 3 747 cargo planes, 40 freight containers, and 20 trucks. The school bus-sized machine comprises 100,000 parts and weighs nearly 200 tons.
So what exactly does this EUV machine do?
Intel co-founder Gordon Moore observed that the number of transistors crammed onto a processor doubles roughly every 2 years, a cadence that has continued for more than 50 years and has long been known as Moore's law. The more transistors and components on chips, the cheaper and more powerful they become. Chip manufacturers use lithography machines to project circuit patterns onto silicon wafers. For decades, they have kept shortening the wavelengths of light on lithography machines to print features for ever smaller transistors. In pursuit of Moore's law, Intel engineers have produced inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. Intel and other chip makers have also adopted processes such as double and quad patterning and water immersion lithography to get the most out of today's 193 nanometer wavelength light. But to make transistors even tinier, the industry needs lithography machines that use radically shorter wavelengths. This EUV machine produces light at 13.5 nanometers. Compared to today's machines, that wavelength is more than 10 times smaller.
So how does this machine work? Put on your best thinking cap, and I will try to explain it simply.
First, extreme ultraviolet light does not exist naturally on Earth, so we have to generate it. Because this tool is so large, it needs 3 floors in the fab. Its laser, about 15 times more powerful than ones used to cut steel, sits on the level below the clean room. A beam transport transmits the laser pulse up a floor into the EUV machine, where a generator fires tiny droplets of metal tin, each droplet only about 1/3 the diameter of a human hair. And that powerful laser, flashing at 50,000 times a second, hits the molten tin. The metal vaporizes into a plasma. This plasma releases light in the extreme ultraviolet range. A collector mirror gathers the 13.5 nanometer EUV light and shoots it to a scanner, where it pinballs off extremely precise mirrors that shape the light into slits that create patterns of transistors and interconnects onto a silicon wafer.
See, wasn't that simple? Just a couple more remarkable facts.
Newer factories at Intel have ceilings 16 feet high. They are raised to 25 feet where these EUV tools rest, because it takes an overhead crane system to assemble the heavy system components. How precise are the EUV machine's optics? Here's the math. It's analogous to an astronaut standing on the moon with a laser pointer targeting the tip of my fingertip here on Earth. ASML is already working on an improved version of the EUV tool that will offer even finer resolution lithography. Intel is currently the first customer in line to receive one of these next generation machines to prepare for the Angstrom era of computing.
Isn't this mind-boggling? Hope you enjoyed coming behind this door to see this marvel of engineering and a tribute to human ingenuity. Thanks for watching. I'm Rob Kelton.
Whenever I show these videos, I also point out a couple of things to my friends and relatives who may not be in the semiconductor industry. You all may know. Number one, point out that the bunny suit that people wear, particularly as we came out of the pandemic era, is not to protect us, but to protect the silicon, right? Because we are the dirty ones. And the clean room is so clean that we have to enclose ourselves not to make that place dirty. And as one of the Rob's video analogies showed, like a laser pointer from moon to pointing to a finger. Another factoid that I read on one of the circuit article is that our wafers, they are so polished, so perfectly flat that if one wafer is of the size of the entire United States, the difference in height between New York and San Jose, California, will be only about 5 human hair width, right? So it's like so perfectly polished, and those are needed for these things to work together so very well. And one other factor I saw is that we use so much of water in all this production, but of course it's all recycled. We don't consume a lot of new water, but just recycled water. And at several points, we purify the water so much that if human beings drink that water, they'll actually die, because it's so pure. If it's consumed, it will suck out all the minerals in our blood into that water, and that could be fatal to human beings. So some such factors, whenever you talk to faculty, friends, give lecture, make it a point to say those, because those images stay in people's minds. Right. I think that's my last slide. So I'll stop here if there are any questions. If not, thank you all for your time.
Sandra, I have a very silly question.
Sure. Yeah, go ahead.
So why the wafer always round? And I know chip always a rectangle, right? So why the wafer they always made of always round like a circle?
Oh, yeah. Okay. No, that when they make that ingot, right? So I think it's shown in one of the initial videos that I included in the meeting invitation. Basically, it's basically equivalent to melting the sand to make silica. When that is done, they put it in a cylindrical that ingot so that it gets heated. I mean, it has to be heated extremely to high temperature. If you make it square or rectangle or something like that, then it may not get heated properly, right? And so when it comes out, it looks like a capsule kind of shape, and after that it's horizontally cut, and as a result the wafer tends to be in circular form rather than rectangle.
Thanks. Because I thought that if you both if the triangle, that's more utilized, you yield better, right? Use all the wafers it could be, right? But the rectangle you always waste a little bit around, right?
Yeah, on the edge, yes, but I think it was from the sand to silicon in this particular video, right?
Then sliced into wafers. Once essentially doubled transistor density in every new generation of products begins when silicon-rich sand is melted and cooled, forming a solid, which is
in this shape. They basically melt and make this cylindrical shape and then cut it up. And
then sliced into wafers. Once inside an Intel fab.
And of course, in the edge, you will lose some, but I think our pieces are all so small. I think each one of the pieces are just like few millimeter kind of size die, right? So the wastage is not that much.
Yeah,
Thank you.
so know that tubular formation is actually part of the process of purification of the silicon as well. As you draw it out of the molten silicon, in order to maintain the crystalline structure of the silicon boule, it's called a silicon boule when you draw it out of the molten silicon. They need to do that very slowly. And so when they draw that out, it has that cylindrical shape as they draw it out of the molten silicon.
Got you. Yep. Thanks.
Thank you.
Okay. I hope you all found that interesting. Thank you all for your time. If you have any additional thoughts or you find any interesting material that's externally available that I could use in my talks, please point them to me. Thank you for your time. Bye.
Yes, thank you.
Thank you.